After that time. Okay. Let's go ahead and cover section 10.2, which is on regression equations. All right. So given a collection of paired sample data, the regression line, which is also called the line of best fit, and is also called the least squares line, is the straight line that best fits the scatter plot of data. And so we're talking about a linear equation. So if you remember from college algebra, the formula for a linear equation in that class was y equals mx plus b. That's essentially what we are setting up here, but in statistics, they have slightly different labels. And they also kind of write the equation in a little bit of a different way. So here we have y hat, which remember, the hat kind of indicates that it's from a sample, right? Not the population value for y, but the sample version. And instead of m and b, we're using b sub 0 as the y-intercept, right? Which becomes b in the college algebra formula. Again, it's this one here. And instead of m, in statistics, they use b sub 1. But that's the slope, right? So this is the slope right here. Now, that's in the textbook for this course. On the TI-84 calculator, they actually have even slightly different labels than this, right? So, I don't know why I used the word even there, but you know, they have different labels in the TI-84. So there's some variation here between the calculator, the textbook, and different textbooks might have different labels as well. So this is just for this particular textbook. And I can't remember, on the calculator it's A and B, but I can't remember which one's A and which one's B. So I'm just gonna wait you guys will tell me since I don't have the calculator to look at. All right, so we need to find, now again, whenever you're trying to find a linear equation, in order to put the linear equation together, you have to have the slope and the y-intercept. So once you find those two pieces of information, you have your linear equation. All right, so the requirements for a linear correlation, this is the same as what we just saw in section 10.1. So I'll just go ahead and kind of skip through that kind of quickly since we just did that. This is the formula we were just talking about. You can calculate the slope B1 using this formula, which is R times, which is the linear correlation coefficient we saw in 10.1, times S sub y divided by S sub x, which is the standard deviation. This is the standard deviation of the y variables from the sample. And this is the standard deviation of the x values. Standard deviation of the x coordinates. And that gives you the slope. And then the intercept, the y-intercept, b sub 0, can be found by taking y bar. You guys want to take a guess at what that means? What's the bar mean? Like x bar, y bar? Mean. The mean. Very good. This will be the mean. So this will be the mean of the y coordinates minus b1 times the mean of the x coordinates. So that's how these values are found. So it's kind of interesting because they both have the mean and the standard deviation as part of their formulation. And this creates a line which minimizes the distance between the points and the line that you're drawing. We're trying to find a line where the distance from every point you have in your data set to that line is minimized. So the distance is as small as we can possibly make it and have a straight line drawn through there. Okay, and so this calculation does that. All right, so it basically measures the distance from the point to the line, and from the next point to the line, and the distance is always positive, but we're trying to draw a line where those distances are minimized in total. Right? If you add up all the distances, this should give us the smallest distance to all the points that we have in our data set from the line that we're drawing. All right. So the properties of the linear correlation coefficient are, I think I messed up here. I can't remember what's supposed to be here, but I copy and pasted that from 10.1, and I made this mistake a bunch of times in chapter 9 and now in chapter 10, so I apologize for those mistakes. These are properties of something, but I don't remember what it's supposed to say. Use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. Use the regression equation for predictions only if the graph seems to be appropriate to the points that you have. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation. So you don't want to put these, I guess for these problems that we're about to look at in the homework, they're going to ask you to construct the regression equation, right? Which is what we were just looking at. Y hat equals b sub 0 plus b sub 1x. This is called the regression equation. They will ask you to construct that, regardless of what's going on in the problem. But you only use this formula if there actually appears to be a linear relationship. If the data doesn't have a linear relationship, then this formula doesn't give you anything useful. It doesn't. It's not very good at modeling the situation, and you don't want to use it for the situation if it doesn't appear to be linear after all. So we will set up this equation, but whether we should actually use the equation or not depends on whether there actually does appear to be a linear relationship with the data that we're given. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. Right? So if your data values, let's say we're talking about over time, and our data values go from like 2000 to 2020 or something. And then we're asked to make a prediction about 2050. Well, that's pretty far in the future from where the data ends. So it probably isn't a good idea to use the equation we have to make that prediction. So that's what this is about. Stay within the region of where your data values actually are to make your predictions. If you're asked to make a prediction about something that's kind of outside of that data set, it's probably not a good idea to use the regression equation to do that. If the regression equation does not appear to be useful for making predictions, so if it fails on one of these things, the best predicted value of a variable is the sample mean. If it doesn't appear to be linear, you should just use the sample mean to make your prediction rather than the equation that you're constructing. So that's going to be the dilemma on a lot of these problems, is they'll say, construct the linear regression equation, which we'll do, and then it'll say, predict. What do you expect y to equal when x is equal to this? And you have to make a decision. Do I use the equation that I just made? Or should I just use the sample mean for y instead? You only use this equation if it actually does appear to be a linear relationship. And you use R to make that determination. Now this is good advice, like number 3 here, but I don't think that it ends up being an issue in the problems that you're going to be given. So, so in real life, you wouldn't want to use the regression equation if the data, if what they're asking you to make a prediction about isn't in the scope of the data that you were provided. But for the homework, I don't think that's going to become an issue. The issue really is going to become, look at the value for R. Does it appear to have a linear relationship? If so, use the equation to make your prediction. If the value of R doesn't appear to have a linear, if it indicates that there isn't a linear relationship, then use the sample mean instead. All right, so let's revisit this data. I'm sorry, we typed it in and then we cleared it out, didn't we? So let's go ahead and type, let's see, we didn't do that one last time, right? And well, let's do this one first, because you still have this data in your calculator, right? The chirps and the temperature. So let's go ahead and take advantage of that. This is already in your calculator. It's the same numbers that we had in 10.1. Find the best predicted temperature at a time when a cricket chirps 3,000 times in 1 minute. Yeah, okay. I don't know, the wording on that's a little bit weird, but I'm sorry about that. What is wrong with this predicted value? So we're going to go ahead and make the prediction, but then we're talking about, so I just said the thing that you didn't have to worry about actually is the issue that they want us to talk about here. But find the regression equation, letting the first variable be the predictor x variable. So we're going to let, let's make sure we're going to do this right. Find the best predicted temperature. So we want to find the temperature, yeah. So we're going to let x be the number of chirps, and then we want to determine the temperature when the chirps are equal to 3,000, right? So same thing we did before in 10.1. The x variable will be our chirps. The y variable will be the temperature. Do the Lin-Rate t-test, right? And, sorry, I don't know why. Nobody ever calls me, so yeah. I don't know how to ignore it. Okay, so what was I saying? Okay, so do the Lin-Rate t-test, and at the top, I can't remember what it says exactly. You guys need to help me out. It has a formula at the top. What's the formula at the top of the Lin-Rate t-test? It's y equals, I should have some, what is it?
A plus bx.
A plus bx, right? So the TI calculator uses this formula for the linear regression equation. So instead of B0 and B1, it uses A and B. A is the y-intercept, B is the slope. I know it's weird because, in algebra, that's not how it was. But then underneath that formula, it actually tells you the values of these components of the linear equation, right? So what does it say the value of A is for this data set?
27.6.
27.6. So this is using the Lin-Rate t-test. It actually calculates the value of A for us, so we don't have to use that formula to do the calculation. And what does it say the value of B is?
0.05.
0.5, 227, 2 2s. We'll just go 0.0523, and then x. So you take the numbers they give you in the Lin-Rate t-test for A and B, you plug them into the formula that they have at the top of that screen, and you put a hat on the y, and that's going to be your linear regression equation. So that's how you do part A. It does all that crazy calculation for you. It calculates R, calculates S of X, S of Y, the standard deviation, I guess not of, but S sub X, S sub Y, finds B sub 0 for you, finds B sub 1 for you. It does all the work for you and just gives you the numbers. Now, I would say if we're going to go, maybe, there's one decimal place in the original data set. We probably should go 2 decimal places here. Why don't we do that? Which means I should go 1 more decimal place for A. So we have 27.6. What comes after the 6? 2. Okay, let's go ahead and do that. So 0.05, okay, that's 2 decimal places, 27.62. All right. So anybody, are you guys, is that what you get also, Miguel? Just to make sure? Okay. All right. So that's part A. Now part B is find the predicted value. So for 3,000 chirps, that's X, right? X is the number of chirps. We're setting X equal to 3,000. You don't have to put in the 1 minute because this is the number of chirps in 1 minute. So the 1 doesn't get plugged into the formula. It's just the description for the data set. X is equal to 3,000. All right. Now we have to decide, to make this prediction, do we plug it into the formula or do we just use the mean? So that is the question here, is which one should we use? And to make that decision, we should look at whether there appears to be a linear relationship here or not. And that goes back to what we already did in 10.1, right? So for this data set, we already found R was 0.87, I don't remember what it was over here. Where was it? I didn't put it on this screen either. Okay, it's right here. So the value of R is 0.8737, right? And the p-value, and so I like to look at the value of R. It's close to 1, which means it seems like it's going to be linear. The p-value was 0.0045. Right? So I guess instead of writing all this on the other screen, it's right here. Let's just go off of this. So because this was the p-value, we decided this does appear to have a linear relationship. There seems to be a linear correlation here. So that means this relationship is linear. And we figured that out in 10.1. Let's just say that. Right? So we should use this equation. Right? So this is the one we want to use, and not the mean. If there's a linear relationship, use the linear equation to make your prediction. If it's not linear, if that was the conclusion we decided, then we would just use the mean of our y values to make our prediction, which we'd have to do one var stats to find out what that should be, right? We do one var stats with that list. It would tell us the mean of those numbers. That would be our best prediction in that case. Right, so we'll plug in 3,000 for x. So we have 27.62 plus 0.05 times 3,000. So if you guys, well, I guess I could do this one on my calculator here. So we have 0.05 times 3,000 plus 27.62. And I'm getting a prediction of 177.62. Which, if we, I don't know, my stat lab should tell you how far to round, but maybe round that to the nearest whole number, because you can't have 0.62 of a chirp, right? Either it chirped or it didn't chirp. So round it to the nearest whole number. So 178 would be our best prediction for the number of chirps. I don't know, that doesn't seem right though. Right? So if you think about these numbers here, these are in the thousands, that's only 178. I don't know, that doesn't seem right to me. I don't know, maybe that, so is it higher, the higher the temperature, the less chirping they do? Is that what the pattern seems to be? It seems like it should be more. So are we sure about these numbers here? I don't know. I feel like it should be a bigger number, not a smaller number. The lower temperature, the less chirping they do. So can we double check these again? You guys did a Lindbergh t-test and make sure this is A and this is B. What you got? Yeah. Huh. I was expecting it to be a bigger number as well. Maybe I was thinking, unless I did my calculation wrong on here, that's possible. So 0.05 times 3,000 plus, no, yeah, I did it right. Because if I take one of these numbers off of here, it should be, it might not exactly equal what's on my chart, but it should be close, right? Oh, wait, no, I'm thinking of this backwards. I'm sorry. Yeah. This is embarrassing. Right, that's not the temperature. This is not the number of chirps, right? I was thinking that's 178 chirps, because I was thinking backwards, but this is of course, it's also a ridiculous answer, right? This is the temperature that would produce 3,000 chirps, right? So the 3,000 is the X value. I'm sorry, I had that mixed up. And our prediction for the temperature that would produce 3,000 chirps is 178, which we don't need to round actually, because temperature can be 0.62, right? So this would be the best prediction for the temperature, which obviously would kill the cricket, right? So that's what's wrong with the prediction. And the point that it's trying to make is, again, the scope of the numbers here is between like 800 and 1,200, right? That's kind of, our data set is kind of, it's valid for that range of numbers. But when you go outside of that range, the relationship might change, right? So if you pick 3,000, which is way outside the range of our data set, you might get answers that don't really make sense or that are not reliable. And I think that's the point that it's trying to make. So it was still the right choice to use this to make our prediction, the linear equation, but you're going to get a ridiculous answer here because that number of chirps is outside the range of our data set and may not even be possible, right? It may not be possible for a cricket to chirp that much in a minute. Sorry about that. I don't know why I got flipped around on that. So any questions? All right, let's go back and look at this example. So for 40 eruptions of the Old Faithful geyser in Yellowstone National Park, duration times in seconds were recorded along with the heights of the eruptions. The linear correlation coefficient is R equals 0.0915. So we don't have to do Lindbergh t-test. They did the calculation for us. And the regression equation is, I'm sorry, didn't space itself very well here, but is given by this. So again, we don't have to do a Lindbergh t-test. They did the work for us. They gave us the regression equation, where X represents the duration time. The mean and the Y represents the height of the eruption. The mean of the 40 duration times is 245 seconds. Remember, X is duration time. So this is the mean for x. This is x bar here, 245 seconds. And the mean of the 40 heights is 127.2 feet. That's for the y value, the y variable, the y value. So the mean of the y's is 127.2 from the sample. What is the best predicted height of an equation with a duration of an equation? I meant to put eruption there. Oh gosh, okay. Okay, supposed to be eruption. You know, as a math teacher, you type certain words a bunch of times, so whenever you start, like, I don't know, equation, eruption sound pretty similar, so I typed equation by accident. What is the best predicted height of an eruption with a duration time of 120 seconds? Right? So that's the value of x they're giving, 120 seconds. But again, we have to make a choice. We have to decide if x is equal to 120 to make our prediction for y. Should we use the equation? I guess I'll go and write that out. Use equation to make the prediction, or should we use the mean to make our prediction for y? Right? We want to know what y is equal to. Right? We have to make a choice. Right? We use the equation if it appears that there's a linear relationship between the two variables. Now, they gave us a linear equation, but it doesn't mean we should use it. We shouldn't use that equation if the relationship isn't actually linear. The point being that you can do a linear regression equation with any set of data, paired data values, right? But it doesn't mean it's a good equation. It doesn't mean it's meaningful or useful or relevant. And so they've constructed it, but it doesn't mean it tells us anything useful. And in fact, that is the issue here, because R is 0.095, and we could look at the critical value, right? So we have 40 eruptions, so n is equal to 40, which means the degree of freedom is going to be 38. We could try to look that up on our chart, right? We have the chart from 10.1 of the critical values. Now, 38 isn't on our chart. This is the limitations of using charts like this. So you just have to pick the one that's closest, which 40 would be the closest one. And whether we choose alpha as 0.05, which would be this critical value here, or 0.01, our value of R is way below that. Our value of R is 0.09 something. And so our value of R, so let's just pick this as our critical value here. So we'll use 0.393 as our critical value for this situation. Going back to 10.2, our value of R was this. So this 0.0915 is way less than the 0.343, was it? 393. Erase. 393. Which means this is not a linear relationship. Right, so if your linear correlation coefficient is smaller than the critical value, that means you should conclude that there's not sufficient evidence of a linear relationship, which means we should not use the linear equation to make our prediction. We should just use the mean, which is, again, and they're trying to trick you here. They give you two different means. So which one should you use? You want to use the one for the y variable because you're trying to predict the y value. So use the y, you want to use y bar to make a prediction about y. So our best predicted value for the height of the eruption would be the mean, which is 127.2. And that's the answer you would type into MyStatLab. Any questions on making that decision? You have to do that on the test. You'll be given some data. You'll be asked, construct an equation from this data, and then make a prediction. But you have to realize that you don't just automatically use the equation that you made to make your prediction. You have to check to make sure the equation should be used by confirming that it's a linear relationship.
Can you scroll up?
Yeah, of course. Go. Is that enough?
Yeah.
Okay. So they give you a value for it. And remember, the closer it is to 0, the less likely that it's a linear relationship. So this is pretty low. It's pretty close to 0. So I went through the formal process of checking it against the critical value. But I kind of knew just looking at it, there was no chance it was going to be linear because it's just such a small number. So that'd be another way to kind of think of it is, now where you have to be careful is if it's like between like 0.3 and 0.7 or 8, then you have to really check. But if it's, I'd say higher than 0.8 or 0.9, it's definitely linear. If it's less than 0.3 or so, it's not going to be linear. That's a pretty good rule of thumb. But answer your, or did you have a question? I didn't know what you wanted
I
to
just
say.
wanted to see the work above.
Okay. Any questions? All right. So we have one more example here. Now here's an example of what the linear regression equation looks like for that data set of 5 points. So you can see it's trying to draw a line that minimizes the distances from the points. Right? So this line is the line with the smallest distance from itself to all the points that are in our data set. All right, so let's find the linear regression equation for this data again. Because I'm recording it, I want to make sure I've done every example in the presentation, even though I kind of feel like this is a little bit redundant. So, but maybe it's good practice. So you want to put this data in a list. These will be your x coordinates. Again, list 1 would be a good place to put that if you have a list 1 in your calculator. This will be the y coordinates for your data set. You can put that as list 2. So it'd be, again, good practice using your calculator, putting the data in, and then do the lin-reg t-test on your TI-84. That'll give you y equals a plus bx. And then lin-reg t-test will tell you the value for a and for b. And even though we're putting this equation together, remember we decided that the evidence wasn't strong enough that this is a linear relationship. But that doesn't stop you from still putting the equation together. But it would stop us from using the equation. So if we were asked to make a prediction, we wouldn't want to use this equation to make the prediction because this doesn't appear to be a linear relationship. And also it's just a matter of practicing, using the lin-reg t-test.
You want R?
We already found R previously. I think it was like 0.59 something, right? But what did we get for A and for B?
1.5.4.
1.5.4 plus
1.7.
1.7. Okay, I think I'll do. Probably should go 2 decimal places, but we'll just go ahead and go with that. So you get those values for A and B from the lin-reg t-test. You plug them into that formula. That's your linear regression equation.
What the rule of thumb on it?
For like what? Like
0.3, so 0.7.
for rounding?
When you find if it's linear or
Oh, okay, sure, of course, yeah. So you would want to use, you could use R, or if since, now the problem we had with this problem here, the issue with this problem, is they didn't give us the actual data. And so they only give us the value for R, and so we can't do the lin-reg t-test here because they didn't give us the information to do that with. But if you can do the lin-reg t-test, then you can either use R, which was the 0.59 something, or what would be faster is if you use the p-value, which remember, we saw that before too. P-value. And see if it's less than or greater than alpha. Right, so the p-value in this case was 0.29 something. I can't remember what it was. 0.29.
Yeah, 36.
36. Right. So now they don't provide a value for alpha, but you can just kind of pick your own in this case. And like I said, most of these problems should be chosen carefully. That if they're not specifying what alpha is equal to, then you should get the same conclusion whatever alpha you want to pick. So I would say if they don't specify an alpha, choose one of these. It shouldn't matter which one. 0.01 or 0.05, and compare that to the p-value. In this case, the p-value is going to be, sorry, I'm doing the wrong thing, is going to be greater than alpha. So the p-value is 0.2936. Alpha, we could pick that to be 0.01. The p-value is greater than alpha. So this does not appear to be linear. That's one way you could draw that conclusion. Because it's not linear, do not use this equation to make predictions, right? You would want to use the mean. So you would take the mean of the y values as your best predicted value for y. No matter, which is kind of weird because it doesn't matter what x is equal to in that case, right? So for any number you give me for x, my best prediction for what y would equal is the mean of the y values. That's your the best guess that you could have, right? Now, if you want to use R, you want to use that chart, which I know we didn't have earlier, but the degree of freedom in this case is 3 because there's only 5 data values in the set. That's n, right? N is 5, so -2 gives me 3. And then, again, pick an alpha, but notice how these values get a lot bigger. So if you don't have that many values in your data set, it becomes like the bar is raised. In order for us to conclude it's linear, it has to be, the value bar has to be really, really high. It has to be a pretty straight line with those 3 points to make that conclusion. And so this would be our value, our critical values. So again, if we choose alpha as 0.01, our critical value would be 0.959. So you compare that back to your value of R. I'm trying to think, because they're both R values. So it's, there's our test statistic R, and then there's the critical value R. They're both R's. But this R is smaller than 0.9, what was it? I can't remember numbers for it. A couple seconds, 959. Right. So this value of R is less than this critical value. And so because that R is smaller than the critical value, we conclude it's not linear. If our value of R from our sample is bigger than the critical value, then that's when we conclude it's linear. That make sense? So yeah, maybe a good way to write that would be if R is less than critical value. Now, the thing, all these examples, we always seem to get R's that are positive. And I think that kind of happens on the homework a lot too. But R can be negative, right? That means there's a negative correlation, but it's still, still could be linear in that case. But for comparing it to the critical value, you just drop the negative sign. So if you do get a value of R that's like negative 0.59, drop the negative sign to make that comparison. So if R is less than the critical value, it's not linear. If R is greater than the critical value, it is linear. For p-value, if the p-value is less than alpha, it's linear. I know, and this is kind of backwards, right? Because here, when it's less than, it's not linear. But here, when it's a less than, it is linear. So it's a different situation. It's a different criteria that we're looking at. If the p-value is greater than alpha, it's not linear. But this kind of has to go back to like what we did in chapter 8, which is the p-value is less than alpha, you reject the null hypothesis. Rejecting the null is rejecting that it's not linear, which means we're accepting that it is linear. Here, p-value greater than alpha, you're failing to reject the null, which means we're failing to support the alternative, which means we're failing to support that it's linear. Okay, any other questions? I'm sorry, I feel like this is not my best job on explaining the material. I have to say, like with chapter 10, I feel like I'm more familiar with the other stuff that we did, like chapter 8 and 9. But also, I don't know, for some reason I feel nervous recording it while I'm teaching. I don't know, it's weird. Like if I'm recording at home, I'm pretty comfortable. If I'm teaching without recording, I'm comfortable. I guess the combination, I don't know, I just feel a little bit nervous about it. So, any questions? No? All right, well that concludes the material for the course. So we're not going to cover chapter 11 or 12. So tomorrow we'll just work on a project. So if you guys can be here, I think that'd be great. We'll work on a project for chapter 8, 9, and 10, which will count as part of your grade, but also help you with making sure you understand all this material from chapter 8, 9, and 10. And then I can be here to answer questions if you guys have questions as well. So I guess I'll see you guys tomorrow. I'll let you guys go a little bit early today. If you have any questions or concerns, please be sure to let me know.